Now let us discuss in detail about the mechanism which is involved in the nucleophilic substitution reactions, that is the mechanism. So generally here two types of mechanisms are adopted to explain the concept of the nucleophilic substitution reaction that are undergone by the corresponding alkyl halides. The first one is, then we call it as SN2. The second one is called as SN1. Here this SN2 is meant to say substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular. Substitution nucleophilic bimolecular. And the second one is substitution nucleophilic unimolecular. Unimolecular. Substitution nucleophilic unimolecular. So what do we mean by the molecularity? Nothing but bimolecular or unimolecular. This we generally already discussed in class 12 about the particular chapter called as chemical kinetics. According to the chemical kinetics, if you come across a chemical reaction, all the chemical reactions may not lead or complete with the same speeds. Some of the reactions will be very, very fast. We can call them as instantaneous. And some of the reactions will be moderate. And some of the reactions will be very, very slow. But if you take a particular chemical reaction, suppose assume a chemical reaction is carried through more than one step. In such a case, every step will never occur through the same speed or velocity. In such a case, what one can observe that some of the steps of the reaction will be slow and some of the steps of the reaction will be very, very fast. And it is observed that according to the principle called bottleneck principle. Bottleneck principle, if you perform a chemical reaction which is having more than one step, in such a case, the overall rate of the reaction depends on the slowest step of the reaction. That slowest step of reaction is generally called as the rate determining step. Simply RDS. Rate determining step of the reaction. So according to that bottleneck principle, if you take a particular chemical reaction, the reaction may have hundreds of steps. But among all those hundreds of steps, definitely only one step will be very, very slowest step. In such a case, the overall rate of the reaction depends only on that particular slowest step. That's why that particular step is generally called as RDS, rate determining step. Now, in the rate determining step of the reaction, if you observe, some of the reactions may involve one molecule or some of the reactions may involve two molecules, like that. So now molecularity is nothing but the number of molecules that are participating in the rate determining step of a reaction, generally called as the molecularity of the reaction. So whenever you come across about bimolecular reaction, that means in the corresponding nucleophilic substitution reaction, the number of molecules that are participated in the rate determining step or slowest step of the reaction is 2. That's why it is called as bimolecular. If the reaction, especially the nucleophilic substitution reaction, if you observe the rate determining step, if the reaction involves only one molecule, then it is called as unimolecular reaction. So in overall, some of the species will undergo with respect to SN2. Some of the species will undergo with respect to the SN1. Because we have different kinds of alkyl halides. The alkyl halides may be tertiary. Alkyl halides or maybe secondary alkyl halides, or they may be primary alkyl halides, or maybe simply methyl halide. So every corresponding alkyl halide will have its own the rate of reaction. It will vary from the corresponding one kind of alkyl halide to other kind of the alkyl halide. That's why the overall the nucleophilic substitution reaction is discussed under two headings of the mechanism. One is SN2, the other one is SN1 mechanisms. Now let us see one by one the SN2 followed by SN1 reactions or mechanisms. The first will take the SN2 mechanism, which is nucleophilic substitution bimolecular. Just for convenience I take here, we have the alkyl halide which is reacting with a nucleophile, which will give the corresponding product as the corresponding product hand along with halide ion X minus. And assume here this is the rate determining step of the reaction, RDS, or slowest step of the reaction. Now in such a case, here if we come across the rate of reaction, so rate is directly proportional to the concentration of the alkyl halide and also the concentration of the attacking nucleophile. So both the case if we come across here, power 1, power 1. If you write the rate law, so rate is nothing but rate constant K into concentration of alkyl halide power 1, concentration of nucleophile power 1. So if I add these two, the overall order is nothing but 1 plus 1, which is second order, and we are saying this is the RDS. In this rate determining step, we can see there are two species which are participating in the chemical reaction. That's why this is the bimolecular reaction. Bimolecular reaction, because in the rate determining step, how many species we have? Here two species. So definitely the rate of the reaction is depending on both the concentration terms. One is the substrate, that is alkyl halide, other is the attacking nucleophile. That's why it is the order is 2 as well as the molecularity also equal to 2. That's why it is a bimolecular reaction. Bimolecular reaction. Let us take in detail about the example with which the SN2 reaction can be carried. For instance, or for convenience, take the methyl halide. Methyl halide. So there are 3 hydrogens here which are bonded to the carbon atom, or we can also show the same thing 3-dimensionally, that is this is the halogen atom, this is the hydrogen atom, and this is another hydrogen atom. Hydrogen and another hydrogen atom. So actually these lines represent that these two bonds are present within the plane of the paper. And this bond represents the particular bond is above the plane of the paper, and this particular one represents this particular bond is below the plane of the paper. So we can represent 3-dimensionally the corresponding molecule. So here which is methyl halide. Methyl halide. Now when this methyl halide combines with hydroxide ion, OH minus is the attacking nucleophile. So when this attacks, the final product here will get it is CH3OH along with X minus. The same we can represent like this also, where we have the OH minus. So this is the attacking group here, this is the leaving group here. Now, when we observe this reaction, what we can understand here it is, we will get one intermediate, nothing but a transition product. The transition product we can write like this. Hydrogen atom, this is the bond above the plane of the paper, this is the bond below the plane of the paper, hydrogen, hydrogen and hydrogen, and here we can observe the leaving halogen, and here we can observe the attacking OH group. So this is a transition state. So this is not the intermediate, this is a transition state. In the transition state, this is the carbon atom. You count the number of bonds around this carbon atom. See, this is a 1, 2, 3, 4, 5. But the maximum covalence of carbon is 4 generally. So you can observe here there are 5 bonds are expected around the carbon atom in the transition state. That's why this is highly unstable. So because of this instability, it is very difficult to isolate the transition state. Now this finally converts into the actual product as this is the OH group, this is one hydrogen atom, and here we can see this is the bond which is above the plane of the paper, and this is the bond below the plane of the paper. All these are hydrogens. Now we can see, if you compare, if you observe this structure and this structure, we check once whether these two are same or not. If you observe, the arrangement of the groups exactly opposite. It's like a inverted umbrella. When the air blows, umbrella can be inverted. So this looks like inverted umbrella. So that means you can observe here both the cases, if you see both the structures are entirely different. The arrangement of the groups. So this product which is formed here, we can call this as inverted product. Inverted product. So whenever you perform or observe the reaction through SN2 mechanism, always will get the inverted product. Okay, and coming to various alkyl halides which will be reacted towards the SN2 mechanism, the order of reactivity will be primary alkyl halides greater than secondary alkyl halides greater than the tertiary alkyl halides. So this is the, from left side we can observe there is a decrease in reactivity with respect to SN2 mechanism. So which will be more predominant towards SN2 means the primary alkyl halides. The least is the tertiary alkyl halides. And here why the tertiary alkyl halides are very less reactive towards SN2 mechanism. If we observe this here in this particular case, suppose if I replace this hydrogen with CH3, that means here CH3 is having the carbon where the carbon is sp3 hybridized. If it is so, this particular arrangement of the groups we can observe like this. So around the carbon also we can see here this is the tetrahedral geometry. Now we can take this hydrogen atom which is above the plane of the paper, hydrogen. Another hydrogen is below the plane of the paper. Now any nucleophile is able to attack here. If you observe, this assume it is also the OH minus group, hydroxide ion. Now if we compare the first case and the second case, assume this is the first case, this is the second case. Now for this OH group is able to attack in this particular carbon atom here, and in this case it has to attack this carbon atom here. Here in this second case there is a bulkiness is there, because CH3 we have 1, 2, 3 hydrogens are there, they also occupies space. So because of this reason, this will experience some repulsion, steric hindrance, which is called as a steric hindrance. That's why in the case of primary alkyl halide, there is no much steric hindrance here, because the hydrogen atoms which are present on this carbon atom are small groups. But when we take the secondary alkyl halide, so we can see here, this is observed on this carbon atom here, the bulkiness is getting increased. This is simple methyl halide. This is primary alkyl halide. Primary alkyl halide, just I am taking here the halogen atom, alkyl halide. Now this bulkiness increased. If you take the secondary alkyl halide, so just I am replacing here the CH3 group. Again this also having the tetrahedral geometry, so that we can observe that this also the tetrahedral geometry. So definitely this carbon will have the arrangement of the groups like this, around this secondary alkyl halide. If you take the tertiary alkyl halide, again this also here we have the carbon around this also, you can see arrangement. So the incoming nucleophile, if you come across, it becomes very difficult for it to attack the carbon which is attached to the corresponding halogen atom. That's why when moved from primary to secondary and secondary to the tertiary alkyl halide, the reaction with reference to or the mechanism SN2 gradually decreases. Now let us take SN1 mechanism. As I told you, this is nothing but substitution nucleophilic unimolecular. So here if I take the reaction as the alkyl halide with nucleophile, we will get the product as RNU with X minus. If we observe the rate of the reaction, the rate is proportional to only the concentration of alkyl halide, but it is independent of concentration of the nucleophile in the RDS, rate determining step. Therefore the molecularity is only one. That's why it is a unimolecular reaction. And coming in detail about this, generally whenever the reaction is proceed with respect to SN1 mechanism, this always involves two steps. Here the first step is generally rate determining step, RDS. Why it is RDS? Because it is a very slow step. And if it is second step, this is fast reaction. As I told you already, the rate of reaction or overall rate, if you observe, the reaction depends on the rate determining step only. Now coming to the case here in the step 1, where I am taking alkyl halide. This particular alkyl halide will undergo cleavage to give the carbocation and halide ion. So here we will get the reaction intermediate as the carbocation, and here this particular step is slow step. That's why it is a rate determining step of the reaction. In this RDS we can see how many molecules are involved here. Only one molecule of the species, which is alkyl halide. That's why the rate is directly proportional to only the concentration of the alkyl halide. In this case the molecularity is equal to 1. So it is a unimolecular reaction. And coming to second step here, this corresponding alkyl halide which is able to form the carbocation, now we will react with the nucleophile to give the actual product. So this is a fast step reaction. Just I told you, among the corresponding alkyl halides, which is more predominant towards SN1 means tertiary alkyl halides. Now let us take one tertiary alkyl halide. With reference to that, we'll discuss about how the final product is able to be formed in this case. Now let us take the alkyl halide, which is CH3 taken thrice CBr. This is tertiary alkyl halide. Now first, this step is a slow step. This is the step 1, which is the RDS, rate determining step here. Now we are able to get the corresponding product as the carbocation. So this is one CH3, another CH3, another CH3. This is the carbocation, along with, here we are taking Br, so Br minus. This is the 3-degree carbocation, tertiary carbocation, which is highly stable in nature, which I already discussed in class 11th. Among the corresponding carbocations, we come across stability is more for the tertiary carbocation, because the corresponding alkyl groups which are present on the tertiary carbocation is generally they are used to release the electron density. So here the stability is more for the tertiary carbocation. That's why among the carbocations the stability order will be tertiary greater than, secondary greater than, primary greater than the corresponding methyl carbocation. Now it is having the corresponding tertiary carbocation. Now this particular tertiary carbocation, now it will react with the corresponding CH3 thrice C plus. Now we take this as the nucleophile as OH minus. Here we will get the actual product as CH3 thrice COH, which is the alcohol. This is how we can observe two-step mechanism which is involved in SN1. So always in SN1 it involves two steps. First step is the formation of the carbocation, and in the second step the carbocation is attacked by the incoming nucleophile. This will give the actual product.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.